Right, we're going to take a look now at the area between two curves. We've been looking at integration, and we've also looked at area and its relationship to area and how integration helps us with calculation. Now, right, so just another quick little recap here. If we want to find the area, right, bound by the function y equals fx, x equals b, x equals a, the x-axis. So this area in here, we're going to establish that. We're going to find that by calculating this long S, the sum of all our fx's between b and a with respect to x. We're going to integrate that, evaluate it between b and a. That's our area. Exact area too, not approximate, exact. Really powerful. Okay, that gets us that area. But what about the area between two curves? All right, well, if we look at this here, you might notice that, okay, we've got a function here, fx, and a gx. Now we've got one that's higher than the other. So if you're just presented with this problem, then you probably think, okay, let's get this whole area here between b and a. So right, this is my task here. I want to look for this area. So my area here, I reckon, would be all of between b and a, wouldn't it? From there to there, underneath the upper curve, the curve that's on top, the higher curve. So as I said, fx. So get that area. Now that is everything between b and a. It's all this area here. And subtract the area that's just under the lower curve, which is the gx curve. And if we did that subtraction, then we would have the area in here between the two curves. Okay, so we just make sure that we evaluate the area, or the integral between b and a of the top curve, and then subtract the one underneath, and that's going to give us the area between those two curves. All right, so that looks pretty good. Let's look at some of the things that come up then with these questions. So we're just going to go to exercise. What are we on? We're on 9K now, and have a look at some of the questions here. So let's have a look at question 2, which says find the area between fx equals x squared and gx equal to the square root of x. Okay, so let's have a look at those curves, and I've just got the calculator up here, just drawn those a minute ago. So x squared is there, and the square root of x. So what I'm interested in here is which is the top curve, and so this is the area in here we want, and the top curve is root x, x squared is underneath it. What's that point of intersection? I reckon it's going to be 1, 1, isn't it? But just let's just go through the motions here and find out what that intersection point is. So we do this, and yeah, there it is at 1, 1. So that's going to be really important for us to get that. So let's model that back on my notes page. So we go in here, and what I've got is I've got this y equals the square root of x, and I've got this y equals x squared, and that's my area in there that I'm after. And I've got this point here, which is 1, 1. Okay, so what's my area going to be? It's going to be between 1 and 0 of square root of x dx. Right, that's the top curve, minus between 1 and 0 of x squared, which is the underneath curve. And if we evaluate that, we'll get this area in here, won't we? Because this integral gets me the whole lot. That integral gets me just this white bit. So I do a subtraction. I'm left with the area in between the two curves. So go back in over here and see how the calculator works for us. That's great. There it is. Now do the calculation. Well, actually, let's do it manually first. So what I'm highlighting here: use of the graphics calculator to help you with the sketches and to see the area that you need. Find the point of intersection, find out which curve's on top, that sort of stuff. Go back in over here. Let's do this calculation. So we're going to take, and we'll do this, and then we'll look at a quicker method, if you like. So right, this is between 1 and 0. This is x to the half, and this is, I can get straight into this one, can't I? This is x cubed on 3 between 1 and 0. Right, and this one will be x to the 3 on 2 over 3 on 2 between 1 and 0, and we subtract x cubed on 3 between 1 and 0. Now at 1, this is going to be 1 to the power of 3 and this is 1, so that's 1 over 3 on 2, which is 2/3. And when you put 0 in there, you've got 0, so you've got 2/3 out of that. You put 1 in there, you've got 1/3 minus 0, so you end up with 2/3 minus 1/3, which equals 1/3. So 1/3 is our area between the two curves. Alright, let's check that using the calculator. We go in, and on this button in here we can use the integral function, and we can put in between 1 and 0, just tab up there to 1, and I'm going to put in here, I'm not going to do a subtraction. What I'm going to do is I'm going to do this. I'm going to put in the quick way. As you know, as you probably have picked up, if you've got, if I've got the integral of f of x plus gx, then I can split that up. So it works both ways. Obviously, I can go this way also, which is what I want to do here, because I've got a subtraction of two integrals. But why don't I just do it all in one? So my area between the two curves actually for this scenario up here in one statement, in one integral statement, is just fx minus gx dx. So we're taking just the top curve and subtracting the bottom curve and evaluating between b and a. Is rather than evaluate two integrals, it's going to be quicker, isn't it? So we're going to go from 1, we're going to go between 1 and 0 here, and we're going to take square root of x and subtract x squared dx. Alright, so let's just see. Alright, so that goes to x to the half. Alright, between 1 and 0 minus x. Alright, so we know the way this is going to go to x to the 3 on 2 on 3 on 2 minus x cubed on 3, all evaluated between 1 and 0. Alright, and we put 1 in there, we get 1 minus a third, and we put 0 in there and we get 0 minus 0. 1 minus a third is 2/3, and that's exactly, no, we got 1/3 there. So what was the error? Put 1 in there, that's 1 minus a third minus, okay, error spotted, that there is, that's 1 over 3 on 2, which is 2/3. So that gives us 2/3 minus 1/3, or 1/3. Okay, units squared. So you can see we've got the same result as that, but we're just doing it in one hit. So this is what we're going to work with right here, just this subtraction as a single integral. Okay, so if we go in and have a look at the calculator, and in our calculator we can just hit, what are we going to do? Square root of x, and then we tab out of the square root, minus x squared. We tab out of that, we hit dx, we go between 1 and 0, hit enter, and we get 1/3, which is what we got. Excellent. Okay, we're going to look at one more example here, and that is on exercise 9L question 1, page 317. Two functions here, a cubic and a quadratic. Let's have a look at the graphs of them, and here they are. Now the interesting thing here is that right in purple we've got the quadratic, and in black we've got the cubic. Okay, now initially if we're sort of working from right to left, high to low, we've got a point of intersection up here, and the purple, the quadratic is the top graph and the cubic's the bottom graph. But then beyond this, as we go right to left, we've got a point of intersection here, and then they switch roles, don't they? So this one becomes the upper and the quadratic becomes the lower. So the first thing we need to do is find out what these points of intersection are. We need to find in two sections what the areas are between the curves here and then over here, and we need to switch places when for this. So it's really important that you see what the graph of these functions looks like. So let's go and find the point of intersection up here firstly. So we'll analyze the graph, go to intersection, and find that point of intersection up there. And we're told it's 3, 9, so we've got 3, 9 there. And we'll go and have a look at the point of intersection over here, which is looks at 1, minus 1. Alright, so if we're going to go, perhaps we want to draw this 1, minus 1 and 3, 9 situation. So go up here. Okay, so I've pulled from the calculator the graph as it sat there, and these areas in here we want this area in here, and we want this area in here, and I think we need to look at them as two separate areas. So let's go for between 3 and what's this, 1. So for this blue area in here, I think we want the integral between 3 and 1 of, now let's think, which is the top curve? The top curve is the quadratic, isn't it? It's 2x squared minus 3x minus the bottom curve, the lower curve, which is the cubic, which is that one there, x cubed minus 2x squared. So x cubed minus 2x squared. Right, so that's going to be what we're looking to integrate. And if we go and do that, so we'll just do a simplify here, minus 3x minus x cubed plus 2x squared. Perhaps I can just simplify that before we go any further. 3, 1, 4x squared minus 3x minus x cubed with respect to x. So that's going to give me that in there. Now this area is going to be, right, this is area. This area in here will be between 1 and this point of intersection is, that doesn't look like it, that's at the origin. If you look at these functions, they've both got zeros at x equals 0. So this is going between 1 and 0. Now what's happened is we've switched, so the cubic is now on top, so it's x cubed minus 2x squared, x cubed minus 2x squared, and we subtract the quadratic, which is 2x squared minus 3x minus 2x squared minus 3x. Right, we subtract that in brackets. Alright, so this is between 1 and 0, 1 and 0, x cubed minus 2x squared minus 2x squared plus 3x with respect to x, and simplifying x cubed minus 4x squared plus 3x with respect to x. Alright, so if we evaluate each of these integrals, then we will find the combined area. So we'll do that, then we'll go and have a look at it on the calculator and we'll check our answers. I'll just pause while we do that. Okay, I've just done one step since I was last recording, and that is just to integrate each of my definite integrals here. So you can see I've gone through and added 1 to the power and divide by, done the same here. I'm going to evaluate each of these now, so I'm going to substitute 1 in here. So I get 1 over 4 minus 4 over 3 plus 3 over 2. And when I sub 0 in, I'm just going to get 0, aren't I? So I'll put minus 0 in there. I'll work that out in a second. Now if I want to put 3 in here, so 3 cubed is 27 times 4 is 108, over 3 is 36, minus 3 goes in there, 3 squared is 9, 3 is a 27, minus 27 over 2, and then I'm going to put 3 in here, 3 to the power of 4 is 81 over 4, and I'm going to subtract, putting 1 in, it's 4/3 minus 3 over 2 minus 1 over 4. I think I'll pause while I do some calculations. Okay, calculations made, all done manually, but this is obviously going in your calculator. I get 5/12 units squared for this area, and once we run this through, we get 32/12 for this long thin area here. So the area is obviously that's the sum of those, so therefore total area is equal to 5 and 32, 37 over 12 units squared. Now that could go in on the calculator. I'll leave that to you to work out. We've utilized the calculator to find out what the graphs look like, where the points of intersection are, what's the upper curve, what's the lower curve. Okay, plenty to take in there. Exercise 9K and 9L are there for your enjoyment, and beyond that it's some volumes of revolution, and that would be just about, and a bit of linear motion as well in integration. That'll come up after exit. Alright, I'll see you soon. Bye.